Hey everybody, welcome to the video. We're going to be talking about section 3.3.1, which is on sine and cosine function values. Primary purpose of this video is to kind of discover where the ordered pairs for the unit circle come from. Again, it's a unit circle. We're also going to be looking a little bit forward to a circle that's not a unit circle with a different size radius. But we have to start with those ordered pairs. And it all comes from geometry class a few years ago. You learned these special right triangles, the 30, 60, 90, and the 45, 45, 90 right triangles. Let me label them a little bit. Okay, and the way I learned these, with the 30, 60, 90 right triangle, we said that there would be a shorter leg, there would be a longer leg, and then of course a hypotenuse. So in terms of like which side is which, the side across from the smallest angle, the 30 degrees, is the short leg. The medium side, if you want to call it that, is across from the 60-degree angle, which is the lower leg, or larger leg. And the side across from the right angle is the hypotenuse, which will be the longest of all. Over in the 45, 45, 90 triangle, this is an isosceles right triangle because two of the sides are the same. So we can say they have congruent legs and of course a hypotenuse, which will be the longest of the three. Hopefully what you remember from a geometry class is that there's a special ratio that these three side lengths always fall in. So the ratio for 30, 60, 90s was 1 to the square root of 3 to 2, keeping in mind that the square root of 3 is about 1.7, so that's like that in between 1 and 2. And they would be assigned to the sides, in order of size. So the short leg gets the 1, the large leg gets the square root of 3, the hypotenuse gets the 2, and depending on like how much information we know about just a random triangle in the coordinate plane, or actually just in a plane, in the Euclidean plane, is that if we have some multiple of those, like if the short leg was known to be 3, then the long leg is going to be 3 root 3, and the hypotenuse is going to be 6. We effectively scale these up. We multiply all three of them by 3. We could do this with any number. It could be a whole number. It could be a rational number. It could be an irrational number. Probably shouldn't be a negative, at least in the Euclidean plane. Over on the isosceles right triangle side, we have two congruent legs, which will be the 1s. And then the square root of 2, which is about 1.4, is going to be your hypotenuse. So again, we can label 1 to root 2, or if we scale it up, this time we'll multiply by, let's multiply by the square root of 3, which we could do. That would make 1 times root 3, 1 times root 3, also root 3, and over here, the square root of 6. Now, why are we doing this? Because if we leap out of the Euclidean plane and into the Cartesian coordinate plane onto an angle that's in standard position, which as a reminder means that the vertex is on the origin and the initial side is the positive x-axis. Here we do have angles labeled in degrees. I'm going to cross those out and put radians in a moment, but we can see that we form like 3 special triangles that relate to these ones from geometry. The first picture to the right is in the same layout as the 30, 60, 90 above. And what's most notable about that is that the hypotenuse side, which is also the radius of our unit circle, let me put like part of a circle here, that's where it would fall. The hypotenuse is going to be 1 because it's the radius. And if it's a unit circle, the radius has to be 1. So what we need to do is actually divide by 2 with all 3 of these sides to come up with the side lengths that we need. Meaning, this shorter leg is going to be the 1 divided by 2, or 1/2, easy enough. The square root of 3 is going to become the square root of 3 over 2. So, putting that together, when we write our ordered pair, this is, by the way, kind of like our sub-goal for today. The ordered pair is going to be made up of, the x-coordinate of this ordered pair is the side length of the triangle that happens to be horizontal. That was root 3 over 2, we just calculated it. And the y-coordinate is going to be how far up it goes, or 1/2. In the next picture, we have the 45. Oh, one more thing. We're grown-ups now, so instead of using 30 degrees, we're going to call this a pi over 6. In the next picture, we have a 45-degree angle, so we have this isosceles right triangle, and once again, the hypotenuse goes from being a square root of 2 to a 1. The way that we go between those is we divide by the square root of 2. So now I could take the other sides, which both happen to be 1, divide those by 2, and in either case I'm going to get 1 over the square root of 2, which you can rationalize to be the square root of 2 over 2. And with the same layout, here's like the edge of the unit circle. That ordered pair is going to be root 2 over 2 and root 2 over 2. This angle, of course, 45 degrees becomes pi over 4. And now we have another ordered pair radian angle combo. And then with our last triangle, this is a 60-degree angle, a pi over 3 in a moment. But that means this other angle up here is 30. So we have the 30, 60, 90 triangle just kind of like distorted a little bit. Rotated, reflected, something like that. The important thing is the sides are still all going to be the same, right? This hypotenuse of 1, or radius of 1, is going to match up with other sides that are going to be 1/2, only this time it's, on the bottom piece, the x side, and the square root of 3 over 2. So we're just like flipping this triangle around. And compared to our unit circle, the ordered pair is going to be x is 1/2 and y is root 3 over 2. And of course, I think I already mentioned it, our angle is going to be pi over 3. Okay, so this is all the logic, this is all the work, this is all the reasoning that helps us identify ordered pairs in the Cartesian coordinate plane on this unit circle. So on the next page, I actually have a completed unit circle, and we'll talk about maybe some patterns, some ways to remember things. But what we have just done is we've just looked at pi over 6, pi over 4, and pi over 3 as radian angles, and found the corresponding ordered pairs on the unit circle. So for pi over 6, it was the square root of 3 over 2 and 1/2, root 2 over 2 and root 2 over 2, and 1/2 with root 3 over 2. This is again, or maybe for the first time, this is the first quadrant. And we're also looking at quadrantal angles, so 0 radians and pi over 2. These guys aren't going to form triangles. The triangles, of course, are formed by a radius and then taking the point where it meets the unit circle and then just dropping a perpendicular down to the x-axis, or maybe in a different quadrant up to the x-axis. But it should always be perpendicular to the x-axis if you're drawing one of these, what you might hear called a reference triangle. To figure out 0 and pi over 2, we can actually just use coordinates, because like I said, if we make a radius to the unit circle, we're already on the x-axis. Like dropping a perpendicular to the x-axis goes nowhere, but we know what that point is. The radius is 1. So for this one, we're going to the right by 1, and we're going up by 0. That's the point 1, 0. And if we do the same thing for pi over 2, we're going to get the point 0, 1. The boxes in this diagram are reserved for degrees. I think we're going to try to stay fluent and use radians as much as possible. They'll be in the next picture, but there's no sense in necessarily writing these. But let's actually jump right to not a blank unit circle that we need to fill out, but a fully completed one, and annotated if I might. Well, here she is. This is the fully completed unit circle. First quadrant is the same as we just put it together. This one, of course, has the degree measures as well. And what the highlighter represents is a bunch of angles that would create similar, possibly congruent, well, I guess they would be congruent, reference triangles. The angles themselves have to be in standard position. So let's really quick look at orange. Orange, we have a pi over 3 that goes to here. And then in the second quadrant, we also have a 2 pi over 3, which, if we created a reference triangle, dropping from the point at the unit circle to the x-axis and kind of like tracing out, we would get something like this. And if this angle is 2 pi over 3, then the angle that's inside it, you might call it a reference angle, is 1 pi over 3. In degrees, if we're not fluent yet, in degrees, if one angle is 120 degrees, the other one needs to be 60 degrees, so that in total we get half of a rotation. Adding those two angles together gives us 180, or pi radians. So the takeaway is, if those are congruent triangles, all the side lengths are going to be the same. The x side, the y side, and of course the radius of 1 are all going to be the same length. The difference is, because we're not in the Euclidean plane, where all side lengths are positive, and in fact, side lengths are still positive, but we're talking about coordinates here. So the x in this triangle does represent a distance of 1/2, but because we're going to the left and we're talking about coordinates, that's going to be a negative 1/2. So looking now at all of the angles in the second quadrant, notice all the same values. Pink matches pink, yellow matches yellow, but all the x's have negative coordinates. If we jump down to the third quadrant, same values for the same three colors, big difference. Both x and y coordinates are negative because we're below the x-axis and we're to the left of the y-axis. And in quadrant 4, only the y coordinates are negative. You could look at the quadrantals as well. Those are easy to figure out because, we can follow the radius distance of 1, find out what the coordinates are. But if we're going left, like we are at pi radians, x is a negative 1. And if we're going down, like we are at 3 pi over 2, we get a negative y. Other things to note in here, all the colors, which we said have the same values, well, in their reduced form, 2 pi over 3, pi over 3, 4 pi over 3, 5 pi over 3 for orange, they all end in over 3. So if we have a reduced form of a radian angle, we can sort of like develop these, patterns is probably a great way to describe it. Similarities, whatever you want to call it, they're going to help you remember these values. So what you could do is you can sort of memorize the values that go along with the x's and y's for any given denominator of radian. And then you could use what quadrant it's in to determine whether the x and y are positive. Now, full disclosure, this is not the way I learned these values. My teacher gave me a table. We looked for patterns in the table, which I could show really quick. And I just kind of memorized them that way. Let's take a look at the way I learned it as well. All right, so the way I learned it, I learned that the table that I have here, which includes 0 and pi over 2 as quadrantals, and then the three angles in the first quadrant that we know. I learned that the pattern was they were all secretly over 2's, and then increased, following a pattern. We said root 0, root 1, root 2, root 3, and root 4, and then some of these simplify. So starting on the left, the square root of 0 is 0, and then 0 divided by 2 is 0. The square root of 1 in pi over 6 is 1, so we get 1/2. The square root of 2 and the square root of 3 do not reduce. The square root of 4 is 2, and 2 divided by 2 is 1. And then because of the triangles we form and some other patterns related to sine and cosine, we can say that the cosine row is in reverse. So if I look at sine on the left, we have 0, so cosine on the right, we're going to have 0. And then moving 1 to the right in the sine row, it's 1/2. So that goes here for cosine, root 2 over 2, root 3 over 2, and 1. So there are some things like I learned that in the first quadrant, sine was increasing. We went from 0 to 1. Well, cosine in the first quadrant is decreasing. And that kind of tracks if you look at the way the behavior of the unit circle works as well. I am leaving out tangent. We will learn soon that tangent is just sine divided by cosine. So something like sine divided by cosine would be 0. and we'll develop that soon enough. But the way that this curriculum works, we start with just sine and cosine. We learn some patterns, and tangent, while it is related, has some subtle differences that we want to distinguish. So we kind of save that for a little bit later. Now, while it is extremely important to learn those values in the unit circle, like we will want to memorize those, they're part of the unit circle quizzes, it's also worth mentioning that not all circles have a radius of 1. So how could we find those ordered pairs if we have a different radius? It's actually pretty simple. We learned in a previous section that cosine is x over r. We learned that sine is y over r. So if we solve these guys, these two equations for x and y, r cosine theta and r sine theta are the coordinates of that ordered pair. And again, the big difference for those is the radius is not 1, it's something else. That means we need to multiply those ordered pairs each individually by whatever the radius is. Now, working with circles that have a radius other than 1 is the main focus of section 3.3.2. But the rest of this section is just like, hey, let's double down on these coordinates. Let's really get them ingrained. Let's look at another sort of a pattern. And this pattern in example 1 and actually 2 and 3 is just talking about some of the symmetry in the unit circle. What they have done over here on the right is they have taken just a generic point P. Because of the coordinates that they give to us, we can say that this angle is pi over 6 because I know the x is root 3 over 2 and the y is 1/2. And what they've done with that is they've reflected point P across the y-axis to come up with Q. I've reflected that point across the x-axis to come up with R, and reflected R or P across an axis to come up with point S. So in terms of like what the ordered pairs are, like Q is just going to be the same set of ordered pairs, but a negative X. So negative root 3 over 2 with 1/2. In R, they'll both be negative, and in S, we'll have a positive X and a negative, but same value, same root 3, same 1/2. And the triangles they form with this little bow tie thing, let's actually look at the second quadrant one, are those reference angles we talked about. The angle from standard position would look like that. And then this little guy here is also going to be a pi over 6, or 30 degrees. The angle in standard position, 5 pi over 6. What they want us to do, if you look at the table, is come up with the angle measure, theta, in standard position, the coordinates that pair with it, and then identify the sine and cosine values. So this is going to be very redundant, if we're being honest. And you could do this a number of ways. We can actually do some calculations like I guess I sort of did with the 5 pi over 6 to identify that Q is obtained when the angle theta in standard position is 5 pi over 6. We can also say we know what the angle that ends in over 6 is in the third quadrant. That's 7 pi over 6. It's also 1 pi over 6 bigger than pi, 6 pi over 6 plus 1 pi over 6. And whichever way we obtain the one in the fourth quadrant, it's going to be 11 pi over 6. For the ordered pairs, every single one of these guys is going to have a root 3 over 2 and a 1/2. This is due to a whole bunch of symmetry, the way these points were reflected, and what we know about the angles that end in over 6. Differences, depending on the quadrant, some will be positive, some will be negative. Point P is in quadrant 1, where x and y are both positive. Point Q is in quadrant 2, where x is negative and y is positive. Point R is in quadrant 3, where both coordinates are negative. And S is in quadrant 4, where the y's are negative, but the x's are still positive. So again, we're kind of noticing the pattern and the redundancy here. As far as like sine and cosine are concerned, because we're talking about a unit circle, the sines are just going to be the y coordinates. If we want to say sine is y over r, that's fine. Y is 1/2 or negative 1/2 in all of these, and r is 1 because it's a unit circle. Or we can just know that when we're on a unit circle, sine is the same as the y value. So the sine of, let's actually write this out. We could say the sine of pi over 6 is 1/2. The sine of 5 pi over 6 is 1/2. The sine of 7 pi over 6 is negative 1/2. And the sine of 11 pi over 6 is negative 1/2. And same logic for cosine, except instead of using y, we're using x. So the cosine of pi over 6 is root 3 over 2. The cosine of 5 pi over 6 is a negative root 3 over 2. Cosine of 7 pi over 6 is also negative root 3 over 2. And then the cosine of 11 pi over 6 is a positive root 3 over 2. Now, I can let you in on a little secret. The secret is a way to remember which quadrants have which, how should I say this, which trig values are positive or negative in each quadrant. You can say something like all, starting with quadrant 1 and going around counterclockwise in the positive direction, all students take chemistry. That one is probably more appropriate because some of you guys are taking chemistry. You can also say all students take calculus. Has a little bit of a math flavor to it. But what this stands for is which trig function is positive in which quadrant. So all of them are positive in quadrant 1. S for students stands for S for sine is positive. T stands for tangent. We're not really working with it right now, but tangent is positive. And cosine is positive in quadrant 4. So this means that all the other trig functions are going to be negative. So in quadrant 2, for example, sine is positive, but cosine and tangent are going to be negative. And we'll elaborate on this as we learn more and more trig functions. What I'd ask you to do now is try to complete example 2 using the isosceles right triangle, and example 3 using the pi over 3 or the 60-degree angle. Complete the table as well. Again, should be a lot of redundancy. Go ahead and do it, and pause the video. I'll show you the solutions in just a moment. And here is the table for the pi over 4 angle, the isosceles right triangles. And for the pi over 3 angles, and you may notice some patterns in, again, the positive and negativeness of the sine and cosine values. The last thing to talk about in this video is where we're headed, what our goal with this is. I do not want to be recreating a unit circle every time I have to evaluate a sine or cosine at a value. So what we want to get better at is just kind of finding a way to conjure up the appropriate values. And I'll tell you the way that I do it. You could also just go with the memorization route. It's entirely up to you. For me, when I'm looking at something like the sine of 2 pi over 3, I think, hey, it's going to have the same number, same numeric value as what the sine of pi over 3 is, but it may be positive or negative. I determine the positive or negative part based on its quadrant, and I determine the numeric part based on the angle, and specifically like the angle's denominator here. So the pi over 3 is a root 3 over 2, and 2 pi over 3 is in quadrant 2, where sine is positive. You could do the all students take chemistry. You can look at quadrant 2 having negative x's and positive y's, but we're going to have a positive root 3 over 2. You don't have to write the plus. I'm doing it for effect here. If I look at the next question, cosine of 5 pi over 4, well, I know the value of a cosine with an over 4 is going to be a square root of 2 over 2. And then 5 pi over 4 is in Q3. And based on that one, we're going to have a negative value here. Eventually, you're going to get much quicker at these. You're going to look at these and you're going to know the answers like almost immediately. You might pause for a second to determine if they're positive or negative, but it's going to be automatic. We're going to do so much of this year, next year, that these values will become automatic. And this is one of those, like, don't sleep on it. The faster you get these into your brain, the easier the next thing is going to be. So I do advise do those practice quizzes. And actually, let's start with these. So take a few minutes to work through the rest of these examples. I'll show you the solutions. And that'll be the end of the video. You can work through the homework as well. And we'll meet again soon.